So thank you very much for those of you in Europe who are watching this instead of Netflix. And so tonight I want to tell you about the work we've been doing over the recent years on odd robotic matter, and which are basically these mechanical systems here that are materials made of robots instead of atoms, and how I will explain how they allow us to explore non-Hermitian physics, so physics in which energy is not conserved, and that leads to interesting wave propagation phenomena which interact interestingly with topology and nonlinearities. And so what I want to show you here, I just want to give you an illustration of two examples. So what you see on the left, if the frame rate by zoom is good enough, is the wave that we excite just by a finger, and that propagates only in one direction, and that seems to be to have a stable envelope and a constant velocity. And you see that the wave actually there is a carrier wave that has like fast oscillations in space and time, and an envelope, and that's the envelope that has a constant shape. And so it looks like the envelope looks like a soliton, but a soliton that is in a dissipative or active medium, so a soliton that only can, for instance, propagate in one direction. So that's one example of that I will discuss at length. A nonlinear wave that is unidirectionally amplified, and on the other side, what you have is a 2D wall made of 120 robots. And what you see is that what we study is the impact of a projectile on such a wall. And during the impact, what you see is that the object is deflected, and a wave seems to be propagating towards the right side of the object. And so the two waves that you see here are two manifestations of non-Hermitian wave phenomena that I will discuss in that talk. So in that talk, I will describe the physics of those waves, and also the principles that allow us to construct this medium. Okay, and so this is what I call odd matter. So let me just define what I mean by odd matter. Odd matter is a class of system in which that are characterized by interactions that are non-conservative and also non-symmetrical. And you have a few examples here. Maybe some of you in the audience know well tight binding models, for instance, and you could think of odd tight binding systems as being systems in which H is non-Hermitian. And non-Hermitian in the sense that you have, for instance, electrons that would preferably jump to the right than jump to the left. In the middle system, you have a network, an elastic network, and these would be springs that would seemingly or effectively break Newton's third law. So springs that would be stiffer in one direction and in the other. And if you had such an elastic network, what you would have at the end would be a dynamical matrix. I would describe its time evolution that would be non-symmetrical. Okay, and if you look at the continuum limit, you can think of viscosity or elasticity, where you have a relationship between a stress tensor and strain tensor, or strain rate tensor, and those would be described by elastic or viscous tensor that would be non-symmetrical themselves. Okay. And so the question I want to address here, okay, is what is the emerging dynamics? Imagine we can make or we can study such systems. What happens? Okay, and what I will argue is that in a lot of very generically, there's a very universal phenomenon that happens, which is called the non-Hermitian skin effect, and that we'll discuss in the first part of this talk. So if you take the textbook tight binding model that you consider to study, for condensed matter, you have a chain of atoms, and the electrons can hop left and right. And usually, by virtue of energy conservation, the probability of the electrons to jump right or to jump left is the same. So usually, the hopping rate GR or GL are equal. Now, let's assume we have a system where this is not the case. So here, these are the hopping rate GR towards the right and GR towards the left, and we assume that these are not the same. And this actually was, I think, first proposed by attenuate and Nelson in '96, and has recently been let's say, a revival of interest because of its interesting interplay with topology and topological insulators. Okay, so this is the simplest odd, let's say, quantum material. You could think of the same for vibrations, not electrons, and this would be a chain of springs. And again, when you look at your Comments method book, you also often start to study phonons by chains of springs. And here you would have a spring that would be stiffer when it's towards the right and towards the left. So that would be a bit weird. If I would push on you through such a spring, you will feel more force than I do, right? And so to do this, I will, yeah. So that's a weird object. I will discuss how we can make such object in mechanics later on. But for now, I want to first focus on well, what happens. So if you look at the spectrum, so you can take your chain, you can calculate the eigenvalues. If the chain is a ring, so if you have a periodic system, you find that half of the eigenvalues have a positive imaginary part and the other half have a negative imaginary part, which means that half of the mode are amplified and the other half of the mode is attenuated. Okay. If you look at the modes, they look like normal phonons, like sine waves, essentially. But what's interesting is that the half of the mode that is amplified actually all have a positive wave vector, while all the half of the mode that are attenuated have a negative wave vector. And so that means that only the forward propagating waves will be amplified, while the backward waves will be attenuated. So if you have such a ring, what would happen is that rapidly you will only see waves that would ever increase, right? So now the question you can ask is, okay, this is interesting, but in practice, I never have I hardly ever have a ring. I only have finite media. And so what happens if I have an edge, right? You can imagine that if you have an edge, the wave will not be able to amplify at some point. They will have to bounce back. But when they bounce back, they will decay and they will be attenuated, right? And so what you will end up having is waves that cannot grow, so they're and cannot decay, so they will become stationary waves. So the imaginary part will become zero. But then they would have a very different eigenmode shape. So you see that here the modes look like ordinary, like vanilla phonons, but here they look like very all skewed, all localized towards one edge, the edge towards which the waves are amplified. So this is very strange. And also you see that here, the only thing I do is I just make a cut in the ring. So, and you see that the spectrum completely changes. And so this is quite unusual. Usually if you do that for a Hermitian system, if you look at the spectrum of the bulk of a periodic medium over a non-periodic medium, it hardly changes when you make a cut, when you take a ring, when you make a ring into a chain. Here, it's drastically different, okay? An interesting thing that I will come back to later is that there is some connection to topology, because now you see that the spectrum, as I increase my wave vector, actually I make a loop in the complex plane. I go here when the wave vector or k wave vector is minus phi to pi, I go around. So when I travel in the Brillouin zone here, I make a circle, right? So immediately you can think of maybe defining some sort of winding number based on this. And that's what people have done. Usually what you can do is you can define a winding number, which is basically defining how this loop encircles the complex plane. Well, the formula here is that you have to wind, so the energy, if the energy winds around an eigenvalue, you have a winding number here of 1. And if you wind but not around a eigenvalue, then you have a winding number of 0, right? So you can, in principle, define a topological quantity here, and people also have, or you can also see a link between the sign of this winding number and the side on which you localize your edge modes. Okay. So if I recapitulate, this is what we have. We have very strong difference between periodic and open chains. And at the end of the day, so you can make this connection with the winding number, but at the end of the day, mathematicians know that very well. What we have actually, what's a Hamiltonian or dynamical matrix, that's a two-pits matrix. So because it's a system that is translation invariant, so you have the hopping parameter or the stiffness that are the same along diagonals. And what is very strange here, what I just insisted on, is that whether you have these diagonal terms, the off-diagonal terms here or not, you have a very strong difference in the spectrum. And mathematicians who have studied the spectral properties of two-pits matrices know this very well. And I think it's only more recently that now physicists have discovered their relevance, right? So that's just a side note. Everything we do here is the physics of two-pits matrices that are non-symmetrical, okay? And so now that what I want to ask is, okay, now it's nice. I have in principle an exotic phenomenon, these unidirectional amplified waves, and there is an interesting discrepancy or strong difference between open and periodic systems. So that's interesting potentially to explore. How do I do this? How do I make this? And to do this, I'm going to introduce odd robotic matter, so materials that are made of robots instead of atoms. And the inspiration is really starts from people who wanted to study animals and locomotion of animals. And you may know this nice work of Purcell in the 70s, who was interested in swimming at low Reynolds numbers. And what he postulated is that the simplest swimmer that can swim forward in low Reynolds numbers needs to have 2 degrees of freedom, because only with 2 degrees of freedom you can break time reversal symmetry and reciprocity. Okay, in the robotic community or physics and robotic community, people actually use a lot now this elementary building block, and that's what we will use. So we will take also a Purcell particle here, and we will make it odd, right? And the way we make it odd, or how it works, is that how you can see that it's odd is I'm going to pull on the left and on the right, and you see that if I pull on the left or on the right, I see something opposite. I see a response that is opposite. So if I just maybe show it once, you see when I pull on the left, the left arm, the right arm opens, but if I pull on the right arms, the left arm closes, right? So this is an odd response. How do we do this in practice? We just use active control. So you have a collections of actuators and sensors and microcontrollers. So every one of those little particle robot here has a little Arduino that you can control. And then at the end of the day, you have a constitutive relations here, the torque versus angular displacement response that is odd or non-symmetrical, because here you have a plus or minus sign. Okay, so that's good. That's the essential building block that you need to construct your elastic network that is non-symmetrical. Okay, so we can use that, and we can make lattices, and we can study, for instance, these unidirectionally amplified waves. So you can look at the response, and what's interesting as opposed to earlier example of let's say non-reciprocal waveguides, is that this really works for all modes. So I told you that all the modes were going to one direction. So here for a pulse, all the modes are amplified towards one side. So that's potentially interesting. And in parallel to our efforts, a lot of people have tried. Oh, there's a question. I don't know if I should stop.
Yeah, I have a quick question. Maybe just because I didn't understand so quickly. So you have a non-reciprocal system. The spectrum is also asymmetric or not?
Yes.
Of these modes, the spectrum is asymmetric.
Yeah. The imaginary part is asymmetric. Yeah.
Imaginary part.
It's not so easy to see because I only plot the projection, but if you would plot, imaginary part of the frequency as a function of a wave vector, you will see it being asymmetric.
Ah, it looks very symmetric.
Yeah. No, that's what I said when I said.
It's because it is 2, not 0 in the middle. Or what? What is asymmetric here?
The asymmetric is that let's say, okay, can I annotate?
No, the annotations are off, but the plot is the plot is imaginary and real components of frequency. No, there's no momentum there.
Yeah. So now I can plot.
Yeah.
If I would plot the imaginary part of the frequency, right, versus the wave vector or the energy, right, I would see something like this. So I would see that the positive wave vector will have a positive rate, and the negative wave vector would have a negative rate.
Yeah. Okay, and then could you specify which symmetries were broken? Because in principle I see the device, but can you specify which symmetries were broken in order to obtain this?
Yes. Yes. So the symmetry we break here in the specific system of the chain, I will show again, is we break conservation of linear momentum.
Only one,
right? So yeah. So if you want to break Newton's third law, you can convince yourself that the third law of Newton is actually synonymous to the conservation of linear momentum. Right. So that's the main, and I do it in such a way that you break also the inversion symmetry.
Okay, so inversion symmetry and then conservation of linear. It's like translational symmetry, I guess.
Yeah. So if maybe it's useful. Is it useful if I write a wave equation? I don't know if you like wave equations.
Yeah, I'm fine with wave equations. Very fine.
So if you would write a wave equation, so I guess D'Alembert's equation is this in 1D. So you have the normal D'Alembert's equation, but then what the addition of this linear momentum here does is that it adds a first order derivative in space like this. Okay, and what you see that this term breaks, it adds linear momentum, and when you add linear momentum, what you do, the consequence is here, you add, you break energy conservation. This is a non-conservative energy, and you also break the left-right symmetry. Yeah.
Okay, good. Okay, thank you very much. Thank you.
Okay. My pleasure. Thanks for the question. All right. I'll continue then. Yeah, please, if you have any question in the meantime, I mean, I don't know what the format is, Anton, but I'm happy to be interrupted. Yeah.
All questions are certainly welcome at any time. Actually, I also have a question. There's something that in the equation you wrote that I actually wanted to ask also before. It seems that you're adding the lowest derivative term, which is also why the dispersion, so basically there's like a square root singularity, meaning the dispersion of the modes close to momentum 0 seems to have like omega square equals k, right? So that is this singularity does this singularity have any interesting effects, like destroying acoustic phonons or something like this? Because here the acoustic phonons decay or explode much faster than they can actually propagate.
I don't know. I don't know. I mean, we battled a lot with the singularity, but is it really creating? I'm not so sure. I mean, in principle, I think you could have a very similar response so long as you have an odd spatial derivative here. So you could have a cubic or quintic. But then I guess those would also give you some singularity, right? I guess.
Cubic would give a mostly decay acoustic phonons almost without decay. So cubic would make acoustic phonons propagate the longest. this actually basically this thing prevents existence of acoustic phonons, or prevents propagation of acoustic phonons.
Yeah, I mean, yeah, I don't know. I mean, I have something to say, but I'm not sure that will answer your question. So, if you calculate the Green's function of this, and actually we did that. In fact, you know, the Green's function for D'Alembert's equation is just double Heaviside, you know, as a function of x, right? And as time goes by, the Heaviside grows, right? And here, what we see is that you basically your Heaviside is modulated by some exponential growth, right? But so I don't know if it's, and so as you know, so what it means that you know the waves blow up on the right and dies on the left. But I don't know exactly if it, yeah, I don't know how to relate it to your question. Yeah.
All right. Well, it was also a vague question, I admit. All right, thanks.
Yeah. All right. So yeah, so we're not the only ones. In fact, yeah, to search for this non-Hermitian skin effect. Pretty much, I think we are the first. Even though we didn't know it was called the non-Hermitian effect, but in the subsequent year, people in Germany here use the electronic circuits. So they use transistors to break the reciprocity. Here they used I think quantum optics. They use a very similar setup also to skew the walks of photons. And here people use the fibers, optical fibers, and acoustic optical modulators. And there's a related work where they look at a similar effect in diffusion. So you can think of this non-reciprocal diffusion here. Okay. And so that's interesting that this effect is quite general. I mean, it's not married to mechanics. It can happen in I mean, anytime you have a eigenvalue problem, in fact, it can happen. And the two questions I would like to address here in the rest of the talk is, what can we do with it? Is there interesting applications? And what at the more fundamental level, what is the interplay with nonlinearity and with topology? Okay. And so I'll start with the obvious. If you have waves that are amplified in one way, you can make unidirectional amplifiers, broadband, right? So that's what we show here in the previous work. I showcase you have 50 decibel unidirectional isolation over like 4 decades in frequencies. So that could be useful. I don't know many applications yet where you want to send waves in one direction, not in the other. Usually you want to shield waves altogether. But at least there is your property. You also have the same in the flexural wave, which work more at the kilohertz regime. And again, that's the optics that I use. You can make maybe unidirectional waveguides for light, or people also have proposed to use that and to construct a scheme to make quantum sensors that amplify more the signal than the noise. So you use that skin effect to amplify the signal more than the noise, and it could potentially become an interesting sensor. Yes?
There's a question in the chat, which also I think fits what you're talking. Is there also non-robotic odd matter? So is it possible to implement similar behavior without active feedback?
Yeah. So what people did, and I think that's along the lines of Ashish Clerk here, what they do or propose at least is that you can achieve that with what they call bath engineering in a quantum So you have, like, for instance, optomechanical resonators. In fact, there is a group at AMOF of Evold Verhagen, where they're able to only do 3 because they work with whispering microgalleries. And then what they do is that they engineer the phase. So they send lasers. So they modulate, for instance, the interaction between 2 galleries thanks to a laser. And if you carefully tune the phase at which you do this, you can also create effectively a unidirectional interaction by also playing with the dissipation. So you need some form of dissipation to achieve this, but you can. So that's the other route I know of. And later in the talk, I'm going to show you that you can also have some pure mechanical version of feedback that don't require electronics, but just pure non, let's say, dissipative or active interactions between the mechanical degrees of freedom of different nature. And I think people also use, have this in the field of active matter. So active matter, where you have swimming particles in fluids, where people are able now, at least in principle and conceptually, to have particles exchange momentum with the substrate, with the fluid, differently in one direction than in the other. I do think, but I don't know, that's maybe more speculative, that maybe biological systems might also be able to have such feature because they're able, through some sensing and biochemistry, to exhibit, let's say, a rectification of the momentum they apply. Yeah. But again, to do this with the electrons, I wouldn't know with the electrons on a time-varying model. Yeah. All right. So, and the other application I'm going to talk about, and actually I'm going to talk about this first because that's the last paper we put on, is you could use this skin effect to achieve or to obtain novel concepts for autonomous and adaptable robots. Okay. And this is actually a work led by Martin Brunnen-Bourget, who was a postdoc in the group and who's now at CNRS Marseille, and with Jonas Venstra, who's a PhD student in the group, and in collaboration with Vincenzo Vitali and his PhD student, Colin Scheibner. And in all these examples I'm going to show you here, we have this, some manifestation of this non-Hermitian skin effect. And what you see here is that you can use that potentially to make a robot exhibit some, basically you can reinvent the wheel. So instead of having like a static wheel that you drive externally, you have some form of wheel that is self-sustained and rolls autonomously. And you can also study, or you can also generate strange response to impact. You see that here I create an impact and I can deflect and amplify the impact thanks to that weird deformations. And this is the first video I showed you before, where you can deflect the impact in an odd robotic medium. Okay, so I'm gonna first discuss about this, and I'm going to show you that actually this odd interaction I talked about connects directly to a concept that actually had been proposed by Vincenzo and Colin last year, which is the concept of odd elasticity. So odd elasticity is the elasticity of elastic materials that have a non-symmetrical elastic tensor. And so if you have this odd interaction here, so this non-symmetrical, this odd, let's say, Purcell particle here, if you make up an hexagon, what you will have is you will have a coupling between two shear modes. So you will have a coupling between the shear mode that you excite when you compress. So when I compress, the structure will tend to shear. So when I shear in one direction, I will tend to create a shear in the other. This is a signature of odd elasticity. So this is one of the first experiments we did. I like always to have this. But if you look at what Colin and Vincenzo had done, was that they formulated a theory of this. And in comparison, we had the question of Victoria before, like which symmetry do you break? The difference between the earlier case where we're breaking conservation of linear momentum and this one is that this one we don't actually break conservation of linear momentum anymore. We don't even, so the only symmetry, I think the only condition we break is we break energy conservation now. And I think that's what the consideration they used to actually derive their theory. They said, what's the most basic way of writing elasticity without having a conserved energy? And what they showed is that in addition to the two moduli in isotropic elasticity, which is the bulk modulus. So the bulk modulus tells you how when you change the volume, this is the pictorial way of representing volume change, and this is a pictorial way of representing pressure. So you see that here the bulk modulus is the modulus that relates dilation to pressure, again, for instance, shear stress to shear strain. What you see is that usually you have this shear modulus that relates how much what's the stiffness, what's the response to, what's the shear stress in response to the shear strain. What you see here is that this new moduli come off diagonal, and now the tensor is not symmetrical. So now so if you for instance shear in this mode, you will create if you shear in this mode, you will create some shear stress in this direction. So this is exactly the manifestation of the picture I showed you. Okay, so that's an interesting way of revisiting basically basic elasticity. And these moduli are really associated to pure non-conservative dynamics, which means that if you, for instance, do travel so if you combine the two modes of deformation, you take your square, you shear it in one mode, then you shear it in the other, then you unshear it in the first mode, and then unshear it. The forces that you have to do are non-conservative. So the area here will correspond to some work that you do. Okay, so this is odd elasticity, and what I claim is that this medium here, this odd robotic building block, is a way to actually create odd elasticity. Okay. What we do here, we go a bit beyond that. Yes.
Sorry, a quick question before we go from the odd elasticity. There's a question in chat. Does it always lead to the skin effect, the odd elasticity, or not universally?
I think that's at least in the cases that I will show, it does. But I wouldn't know to say. I wouldn't know whether it's necessarily always the case. Yes, and I don't think they saw it in that earlier paper for some reason. So it might be that if you consider like really, yeah, I don't know. Yeah, I think it does, but again, I cannot be super absolute about this. Yeah.
All right, thanks.
Okay. Yeah. So now what we will explore, in this work, in the impact and locomotion, is not only the linear or the elasticity, but what happens non-linearly. And when you have this odd modulus here, what can happen is that you can become self-sustained. Your modes can grow. And if your mode grows, eventually it's going to be saturated by nonlinearities, and you will have limit cycles. And here, for instance, if you have this 2 degree of freedom in this Purcell particle, this limit cycle will correspond to work. So there will be, the area enclosed by these 2 degrees of freedom will correspond to work that you do. This is the same here, but in a hexagon. And you see here that essentially your hexagon shakes around, exhibit the self-sustained excitation between these two shear modes, and you see that it leads to a cycle. Okay. You can even study what happens for larger rings, for instance, and then you have interesting nonlinear stationary states that emerge, and that actually we're still busy trying to describe and understand. Okay. The main question I want to address is, okay, now you have those work cycles, so you have odd elasticity that leads to work cycle, and non-linearly you can actually have self-sustained work cycles. Okay, how does it couple to the environment? What I showed you is that in principle you can use that as a principle to locomote, and indeed if you have this hexagon that undergoes this work cycle is chiral, so basically you can rediscover or reinvent the wheel like this, but it's not a wheel that is externally steered. It's a wheel that is autonomous and deformable. So in principle, it's a bit more adaptable than a normal wheel, as it's powered really by a cycle of shape changes here. Okay, locomotion is a bit hard to understand. So if you want to really understand the interaction with the environment, what we prefer do, or what we chose to do, was more to focus on impact, which is a unique collision, and then you can really better capture the exchange of momentum, or how the odd elasticity and the fact you don't have conserved energy actually affect transfer of momentum during a collision. I I hope. And what you see is that if you have one sign of the gain, you deflect left. If you have no gain, you don't deflect. And if you have a right gain, you deflect to the right. So it's a bit like you would, play tennis, right? So if you want to spin a ball, when you play tennis, you have to actually move, your racket basically to create a spin and to deflect the ball. So it's the same case, except that here I didn't have to move my racket. So the additional momentum purely comes from the interior dynamics, let's say self-sustained dynamics of the object. And I'm going to show you that it comes from the skin effect. Okay. And so to do this, I just play the same movie again, but slower, and I reconstruct the deformation, instantaneous angle of the object, as well as the two lowest Fourier mode, which corresponds to the shear deformations. And so what you see is that during the collision, you have a wave that tends to be amplified, right? And as it amplifies, it first cues the object, so the object becomes asymmetric. And so since the object becomes asymmetric, you create this coupling between the two shear modes. And as the object is asymmetric, it becomes one-footed. So you have a symmetric object, but then the object decides to just put one foot. And so since you bounce on one foot, then immediately you induce some angular momentum and transverse linear momentum to that object. I see a question: how do you measure shear 1 and shear 2? So basically, you can look at the deformations of this object, and if you can decompose it into Fourier series, and the two lowest Fourier modes corresponds to the shear 1, shear 2. So if I have an object, shear 1 is this, how much it flattens, and shear 2 is how much it flattens with an angle pi/4. Okay. And so I can show, maybe play it again slowly. So here you have you smoosh the object, and then the skin wave, the wave starts to propagate, and you see that here, as you start to propagate, I don't have the pancake, flat pancake. I don't have shear 1 anymore only, but I also start to have shear 2. And you see that now I'm really a one-footed object, and now I can, if I bounce on the left foot, then I can create a kick that I can create additional linear momentum and angular momentum. Okay. If you measure how the momentum, let's say how the wave propagates, so the amount of energy that travels inside the object, that's what you see. You see that here you have a wave that travels in one direction, and here a wave that travels in the other direction. If you model your ring by a linear fiber, so this is a fiber that has a partial differential equation that is quite a bit that is essentially another flavor of the one I wrote before. So this is an equation that will have quartic terms and quintic terms, but that still will have this non-reciprocity. You can actually predict with, I think, a single fitting parameter, this black curve here that describes very well how the energy travels in one direction. Okay, so that's a way to rationalize with continuum mechanics or wave mechanics what we measure. And you can even use that to actually construct or predict the impact property. So this is the momentum transfer. So basically, how much momentum you gain in a vertical direction and how much momentum you gain in the horizontal direction as a function of the gain. This is the gain here. And this is the data. You see that here I bounce right, here I bounce left. And whenever I have some gain, I actually bounce a bit faster vertically than what I did bounce in the passive case. And you can construct a very basic, a high school model based on this fiber that will predict this odd elastic behavior, this coupling between compression or shear in one direction and shear in the other. And you get those black lines that actually predict the data quite well. Okay, so it's interesting from the viewpoint of robotics, this skin wave physics, because actually we have now a predictive leverage. Usually in robotics, you don't play with the, let's say, continuum objects like this. And so it's interesting that we can actually rationalize what we see by continuum mechanics and actually predict the impact property. So it could be, I don't know, I don't think it's ever going to be used as a competitor of Boston dynamics, but it's an interesting concept that is, just new with respect to what's known, I think, in robotics. I showed you a ring that has 12 unit cells. We also can go nuts and have more of those units. And now we have about 120. And that's what you see here on that video. And we can start to not make it bounce, but actually project or throw objects at this and see what, if the physics is different or is the same. And it turns out that it's quite the same. So this is the wall. And here I reconstruct the shear strain profile as a function of time. And what you see is that actually the wave is quite asymmetric. You see that more energy here tends to go towards the right. Okay. And if you can reconstruct the shear 1 versus shear 2 locally and take the average, and you also see a cycle. And see here more energy. So there seems to be a wave that is amplified towards the right. And the object is deflected accordingly. Now I'm going to run the same movie again. But taking the other side of the gain, and what you're going to see is the opposite. The wave is going to be amplified towards the left, right? And the shear cycle occurs in the other direction. Okay, and so what you can do is you can take the theory of Vincenzo and Colin, the odd elastic theory, but look at, for instance, what happens under a point response. And you see that indeed, if you had a point response, or really like the classic, Lender-Lifshitz or elasticity textbook exercise, and you see that indeed, if you have a response to a point response, will actually lead to a skewed symmetrical, skewed strain response, pretty much a bit like we see here, and pretty much what we see here. Yeah. And you can also look at Rayleigh waves. So, Rayleigh waves are waves at the surface of half-infinite media. And so interesting here, the Rayleigh wave will also have a skin effect. So they will also be skewed towards one direction. And that's what you see here at the end. You see that the wave tends to be localized rather on the right, right? So at least to come back to the question of Mo, at least if you look at the half-infinite plane, you see some signature of the of the skin effect in the odd elasticity. I think before what they did is only look at the full homogeneous medium, and then maybe it doesn't emerge. But here you have like interfacial waves, or Rayleigh waves, and these become asymmetric. So these become let's say spiced up by the skin effect. Well, you can also predict, you can also look at this, or attempt to measure this decay of the wave, and that's what we see experimentally. We see that the waves, or the energy, the vibrations are localized on one side or the other, and that's what you can also use these Rayleigh waves to actually predict the corresponding localization rate, and you see that indeed as you change your elastic modulus, your odd elastic modulus, you actually go from one side to the other. Okay, so that's it for this let's say digression on how we can use the skin effect to actually think about applications in. I mean, it was very brief on unidirectional amplifiers and possibly robotics. In the time I have left, I would have liked to discuss about skin effects versus topology, but I guess I'm looking at Anton here for timing. In terms of how much time do you think I have?
Yeah, easily 15 minutes, so that's quite
easily
fine.
15 minutes. Okay, I'm gonna cut some details and just tell the basic story. So I told you there was this Hamiltonian proposed by Hatton and Nelson in 96, which already was looking at this Hamiltonian that was non-Hermitian, so that has hop-in rate that was not equal equal in one direction and the other. But I think this has really been revived, I think in 2018 and since 2018, because people were interested in topology. So in time binding models that have topological properties. And what people were really interested in is that because of this very large discrepancy between the periodic rings and the open chains, then the whole concepts of bulk edge correspondence comes into question, because usually the bulk edge correspondence assume that the bulk spectrum will remain the same whether you have a ring or a chain. The only thing that changes is additional modes at the edge, but the rest of the spectrum shouldn't change, right? Now, okay, what happens now if you have if you already, because of that skin effect, you have very strong discrepancy between the spectrum in a ring and in a chain. That's what those people studied. So here is in blue is the spectrum as a function of one of the hopping parameters, and for a ring, for a chain, and in gray it is the same but for a ring. And usually when you do topology, you're interested in topological transition of when you close the gaps. So these are the gap closing is when these curves go to 0 here, and usually you argue that you have a topological transition when you have a gap closing. But you see that depending on whether you're in a ring or in a chain, the gap closing doesn't occur at all at the same value of the parameter. So the red here are the edge modes, so the modes that are topologically protected when you have a chain, and you see that you can do all your winding number based on the gray spectrum. Oh, but then it doesn't help you predict when the edge modes appear when you have an open chain. So how do you do that? All right. So what people have proposed here is different approaches of how to solve this. Basically, one way to solve this is to make sure you look at the correct observables, so you don't necessarily look at the right eigenvectors or the left. So what Corentin was proposed to actually define the observable based on the bi-orthogonal expectation value. What Lee and Tomale and Yao and Yan did is they found a way to actually rewrite this Hamiltonian, the blue one, to correct for this unidirectional amplification and come up with a predictive a way to predict this gap closing even when you're open, when you have an open chain. And so I think this problem has been solved. So people now are able to predict when the gap closing will occur based on this. Okay. One thing that has not been described too much is where the edge mode go. So in some cases you have an edge mode on the left or on the right, especially when your chain is odd. When your chain is even, you have either 2 modes or 0. But when your chain is odd, your mode is either on the left or the right. And those arguments here didn't really account for that. And that's what we discussed. That's what I will discuss later. I don't have time to go into this, in fact. This is coming back to the argument of topology I was making. What I just want, I don't have time to make the story complicated. So what I want to tell you is just a way in which actually the combination of topology and skid effect can help you predict where the mode is. Okay, and this is based on this mechanical analog of this SSH chain that is then non-reciprocal odd. Okay, this was done with by Ananya Gatak together with Martin Bronnenberger and Jasper van Vessel. And so the idea is the following: if you have this SSH time binding model, Kane and Lubensky have shown some years ago that you can construct a mechanical analog of this that is described by the same Hamiltonian. And instead of looking at where the electrons are, you look at where the object moves. So this is a chain of rotors connected by springs. The only thing we did in a way was to, if you start from a non-reciprocal SSH chain with non-reciprocal tight binding parameters, what you end up having is a non-reciprocal or odd Kane-Lubensky chain where the springs here are springs that seemingly violate the third law of Newton. Okay, And then you can ask yourself, now that I have this, these complex eigenvalues, I can define a winding number based on how much I wind, how my eigenvalues wind around one another in the complex plane. So you see that here, the two roots of my block Hamiltonians are independently swirling around one another. But here, for some region of the parameter space, you actually see that they wind around each other. And so that you can actually define a winding number that will then go from 0 to 1 as you transit from this spectrum to that spectrum. And what we found is that this corresponds to having the topological edge mode of the Scaling-Lubezki chain on one side versus the other side. And this is the side, this is the floppy side, this is the side that's supposedly stiff, but that somehow the skin effect brings back to the stiff side. Okay. You can actually measure also not only the edge mode, but you can measure you can measure actually the spectrum. So you can measure the winding number directly. So that's what we did with those relaxation experiments, where you can measure the imaginary part of the frequency and the real part of the frequency. And you can also measure the edge mode. So that's what happens with this experiment here. You see that you move here on the right, while in the bottom, you will move more on the left. Okay. If you measure the winding number as a function of your non-reciprocity, non-reciprocal gain, you see that you will jump from 0 to 1. And if you look at where your mode is localized, you go from localized to the right to localized to the left. Interestingly, this doesn't happen at the value that is predicted by the earlier papers that I mentioned that were trying to correct for the gap closing. So the gap closing based on the error paper I mentioned doesn't occur at the same spot as this one opens. So this one, this corresponds to when the gap closes in the ring, in the open chain, but actually in the ring, the periodic spectrum exactly gives you the location at which your mode changes side. In short, what happens is that when you transit, I mean, I think that's something we only recently understood. There's two things that happen at once here. When you go from one to the other, you actually have your edge mode that is protected by chiral symmetry that is locked in the middle. And when you change your parameter, not only your chains, your two roots will wind around one another, but they will also wind around the eigenvalue that is in the middle. Okay, so these are the two, let's say, possible explanations for this. Either this is the skin effect topology, where you wind, you have a transition depending on whether you wind around your eigenvalue, or this is kind of the winding of the two roots around one another. And I think we cannot answer that question based on the system because the eigenvalue always happens to be locked in the middle. But we have now evidence in a slightly different system where actually the mode here can travel, can just transit from being inside to outside. That's actually the upper. So it's really more skin effect that is responsible for this topological transition here that you hear. So that's it for now, and I think I should just stop. So I want to go towards the end. We study, as I was mentioning, soliton and breathers and in these non-reciprocal media. I also wanted to briefly mention, to come back to the comment of whether we actually need feedback. That not necessarily we need feedback. This is an example of the group of Olivier Dauchot, who actually is or was in the audience earlier. He is in the audience. Actually, you here can have a non-reciprocal odd coupling between the two different degrees of freedom of that system. One degree of freedom is the displacement of each node, and you see that in each node you have a little particle that has an orientation, a spin, and so there is a non-reciprocal odd coupling between the displacement vector of each node and the spin of each particle. And so that's a way to use purely mechanical feedback with this active system here. And so with that, I'd like to conclude. So there's basically, yes, it is chiral, and there's actually a symmetry, a spontaneous symmetry, breaking of chiral symmetry in that earlier system. So it moves in one direction or the other. That is distinct to what I had before, where the chiral symmetry was explicitly broken by the robots and the odd elasticity. So that's yeah, here, yeah, the spontaneous symmetry, breaking of chiral symmetry due to this non-reciprocal interactions between spins and displacements. So yeah, to conclude, so it's fun to play with robots because they allow you to create, to break the basic assumptions of reciprocity you have, for instance, at page, let's say, 2 of the Landau sheets. And so you can revisit continuum mechanics, you can revisit wave physics, you can revisit elasticity of networks, and because of that, you can make connections with topological physics, topological mechanics that use let's say floppy modes or zero modes of these elastic networks. There's a lot of prospects to use those odd robotic media, for instance, to think about new design principles for robotic functions like impact, locomotion, and swimming, and so on. So with that, I'd like to conclude and take any more questions you might have. Thank you.
Thank you very much, Corentin. Really, really nice work, and it's also I've been disconnected from the field for a few years, and it is fascinating to see all the things that have emerged. So perhaps to start with the questions, I wondered, do you know if anybody considers mechanical motion of a medium with an active background? Say, imagine yes. I have a just a driven background, which by itself does not do anything smart, but that can break reciprocity to a medium which is deposed in it, or something like this.
Yeah. So I know of work where people do that, but it's very complex system. So they look at a network of gyroscopes. So maybe you know the gyroscopes of William Irvine, right? And then they say, okay, assume these gyroscopes are in a bath of active swimming colloids. And so, you know, the gyroscopes break time reversal symmetry, and the colloids break, you know, energy conservation. And then you have similar phenomena of these waves that can be rectified and propagated in one way. Mm-hmm. So that's an example that I know of.
No, I can add also example, actually.
Yeah.
I mean, there is the spatio-temporal modulation of medium that leads to non-reciprocity, and actually this is a good thing because it can be applied to media, not to like robotic or like electric circuits or other many things which are done nowadays about non-reciprocity, but actual medium, and that looks already good for this condensed matter theory systems, because then you can do something to the material. So it's a spatial-temporal modulation of actual material, and I don't remember which years are the reference.
But, if you want to be out of equilibrium, you need then to do that close to parametric instability, I guess, right? So you need to be, I mean, in the optical resonators, if you have to do that close to double the frequency, right, to be able to amplify input energy, right, because otherwise you're always at equilibrium, right?
No, I mean, it's basically you squeeze the material with some kind of time modulation.
Yeah. But you have to do
yes,
this.
This violates equilibrium. Yes, sure. But let me tell you. I'm just soon my paper will appear on arXiv, hopefully. And there will be all these references, but I can tell you, so Trinity Rosen, New Journal of Physics, and then Scientific Reports, Zaniani, 2015. The Zaniani first author seemed to produce papers on this topic, and also Alu, 2021. I forgot the first name of the guy, Andreas or something like that. He's a young professor, I guess, or group leader. So you can look up these references, and this is about the spatial temporal modulation. Seems to be useful for our science. Okay, sorry.
Thanks, Victoria. I see also a request. Yeah, please do share the references in the chat. These seem relevant. Are there any other questions?
Well, I have a question. May I ask, please?
Please.
Well, hi, Corentin. Thank you very much for the presentation. My question comes from mainly about the odd elastic matter. So on the slide that you were presenting, the odd elastic matter in the paper by Colin Schreibner et al. So in the elasticity tensor, my question comes about the elements of the tensor. It might be a bit detailed,
let me try to pull out the slide again. Hopla. Yep.
Yes, please. Yes. So my question is about the elements 1, 2, and 2, 2. So they are 0, and so it means that we don't have, yes, so it means that for element 2, 2, it means that we don't have any coupling between the, actually it means that we don't have a rotational stress coupling to the rotational strain. How does it mean?
Yeah. If you want to do elasticity, usually, you know, if you have a block of object, there's no stress associated to just rotating the object. That's why it's 0. You take a piece of elastic solid, you just rotate it. There's no stress associated to that, right? The A here is a bit weird because that means that if I dilate, then I have a torque density, right? So that's one way in which this one is still allowed, but to realize this one, you need to inject angular momentum, right? So you have a medium, and then you stretch the model they use in their paper is you take a spring, you stretch it, and assume that you have some form of mechanism that wants to make it rotate when it's stretched, and rotate in the other direction when compressed, right? But for that you need a torque, an addition of. You need to break conservation of angular momentum. Right? Yes. For the K knot, you don't. Right? For the K knot, you don't need a net momentum, and that's what we have. We don't have addition of net linear angular momentum nor linear momentum here.
Yeah. Okay. And the other question is about the third actually type of this deformation, which is the shear one, which you have defined here. So. In terms of, for example, a compression, because of the Poisson's ratio, we will get such actually a stress in a material. So I was wondering, what is the correlation between the dilation and this lateral deformation? How do you consider the Poisson's ratio in this definition?
The Poisson's ratio is given purely by a combination of the bulk and shear, so B and mu. So if you do an experiment where you don't do pure shear, so if I just indeed compress like this, right? Then indeed what I do is I do a combination of volume change and shear one, right? So then the response will not only be given by those terms, but will also have a little bit of the bulk modulus inside. Yeah.
Thank you.
If you have, and what we do, we work in the limit where the B is actually much bigger than this. So we work in an incompressible limit where this doesn't matter at the end. But generically, for any mechanical, experiment you would do, you would have to consider a combination of these strains and combination of those moduli.
Okay, thank you. And one question about the last slide that you showed about the chiral structure. So
yeah. So actually here, I think.
Yes, exactly. So in this case, the actuation, so you are inserting energy because this is non-conservative and you're actuating the nodes.
Yeah. So here what you are doing is each particle is polar, so it has a little field here, and it's walking on the floor, so it's injecting momentum aligned with its polarity. Okay, and yeah, so does it and when it does this, it pushes the cage around it, so it deforms the springs around it, right? But then, so it's interesting because there's a non-reciprocal outcoupling between this polarity, because the polarity here deforms the object, but there's also an interesting mechanism that does that when the object moves, it also reorients the spin, the particle. So you have this double coupling between the vector displacement vector and the polarity. And this coupling is not necessarily reciprocal. So your polar spin entrains your displacement, and your displacement reorients your spin, but not in a symmetrical way. And that's I think this non-reciprocal way that kind of leads ultimately to this bifurcation where you have this spontaneous break spontaneous breaking of chiral symmetry. And then I can show you the movie again. So you will all units will synchronize, and turn clockwise or counterclockwise. Here or here, ultimately. Yeah, does it answer your question?
Okay. So in this case, these moving mechanisms in these nodes, they are all moving clockwise or counterclockwise. So they are all in the same direction.
Yeah. They are all in these two movies. Yeah.
Is there any relation between the compression of the elements, I mean the ligaments, with the angle of this moving part in the node? Same as the relation that was defined in the paper of the odd elasticity. That's the radial strain was correlated with the rotation.
No. It's different. I mean, it's different. the coupling between those two is actually nonlinear, and so it's not at all like odd elasticity. If you want the essence of odd elasticity, you have a non-reciprocal outcoupling between 2 degrees of freedom, and the 2 degrees of freedom are the shear modes, and here the 2 degrees of freedom in that system are the displacement of the particle and the polarity of the active agent inside. But then the analogy stops there, I think.
Thank you very much for the explanation.
We perhaps have time for one pressing question, if any? No, I don't see any questions. So thanks a lot once again, Corentin, for an excellent talk, and thanks everyone for coming. See you.